In this example, we have an amorphous silicon film on germanium. At first glance, we know that the film is reasonably thick, at least a few hundred nanometers or so, due to the number of oscillations in the transparent region. We also see that the film is opaque below about 600 nanometers because the oscillations dampen and disappear completely. We're going to build this model from scratch. To do so, go to the Model panel, click Open. From the Basic folder, choose blank.mod. This opens an empty model where we can enter each material layer by layer. We know that the substrate is germanium. I can click None. From the Semiconductor folder, search for germanium. With the substrate entered, we can add our film using the layer command Add. Click once above the substrate, and then from the Semiconductor folder, choose Amorphous Silicon Parameterized. There are many other values here for Amorphous Silicon, and several of them would work fine. Amorphous Silicon Parameterized is a very general material file that you can choose. In this material file, the amorphous silicon is represented by a Cody-Lorenz oscillator for the absorption, and the index is determined through the Kramers-Kronig transformation. I'm going to enter in a starting thickness value. I'm just going to guess 100 nanometers. With this value entered, I can generate data to see if I'm close. I notice that the number of oscillations in the model-generated data are far fewer than the experimental data, so I need to increase my film thickness. Hold the mouse over the thickness value, press the Shift key, and scroll the mouse wheel up to increase thickness and therefore increase oscillations in the data. And I'm going to do this until the curves closely match the experimental data. This occurs somewhere near 900 nanometers. Now that I have a close thickness and close optical constants for the amorphous silicon layer, I can turn on all my fit parameters, right-click on the thickness, and then we can right-click on the oscillator parameters. In this case, I want to fit for all of them, so I can simply choose Fit All. For many amorphous silicon samples, this is going to be fine to fit all of the Cody-Lorenz oscillator parameters. Now from the Fit panel, choose Fit, and the software has adjusted all of our fit parameters to try and better match the experimental data. We still do not have a perfect fit. One thing that we know is that amorphous silicon will usually oxidize, so we're probably missing the surface layer in our model. I'm going to go ahead and add that using the layer command Add. On top of the amorphous silicon layer, click once. And again, from the semiconductor folder, we can choose native oxide. This is ntve_jaw.mat. In this case, we can't adjust the optical properties, but we can right-click on the thickness to fit. Now we have an almost perfect match to each angle of our experimental data. The native oxide thickness is typical for these materials, about 2 nanometers. The amorphous silicon optical properties are very typical. It's what we expect for amorphous silicon. And this fit is complete.